Hi, today we will be talking about Lab 4, which deals with oscillations. In this lab, we will be observing a mass on a spring as it moves in both the x and y directions and quantitatively describing that motion using Newton's principles, in this case the motion principle and the energy principle. Using Tracker, data points in the x and y directions will be extracted and saved into a CSV file that will be used later, and then we will model a Python program to represent the observed motion in a computer model, and also compare it to the model to see how well they stack up together. And the result was that the model motion very similarly described the observed motion. Here are the physics involved. We have derivations of Newton's second law here, which rely on these two formulas that we'll use to find F net and then find a position data. And then we have Newton's energy principle, which is new for us. So we have delta E is equal to work plus heat, which is also equal to kinetic energy plus the potential energies of gravity and the spring. And here we have the formulas for these three energies. Other formulas we'll use are derivations of Hooke's law. So these are formulas for both the period of oscillation for a spring, which is equal to T, the spring constant, and L naught, which is the relaxed length. And I'll show how to find an average oscillation right now. So when we look at this tracker video, we can see that the spring oscillates in both x and y directions as it is moving here. In order to find an oscillation in the y direction, which is what we use for the calculations, we look at a time around right here, which seems to be 3 oscillations from the beginning. So we take this time, divide it by 3, and that is our average oscillation period, which was calculated to be 1.52. And then we go ahead and calculate K and L naught using that value. So we go to our code now. Here are some initializations. Ball mass is 0.402. The ball position vector is right here, which is in relation to the origin, which is at the top of the spring, and we have an initial velocity of 0. Other initializations: a delta t of 1 over 210 seconds. This is and keep in mind that this is small compared to the time step used in the video. We have G equals 9.8, and these are the values of K and L naught, which were calculated from the T, or the period of oscillation. We have S, which is calculated from the magnitude of L minus L naught. S is the stretch or compression of the spring, and then we have initializations for each energy. All right, so in this loop, we use these initializations in order to find a new ball position, which is at the end. We find the forces for each time step. We add those together to get the net force. We calculate the ball velocity using a derivation of Newton's second law, and then we find a ball position for each time step. We find a new spring stretch or compression at each time step as well, using the same Hooke's law that we saw in the beginning, and then we calculate a delta K, delta UG, and delta US for each time step. And we plotted it. So after running the code, this is what the model looked like. You can see that the model has oscillations in both the x and y directions, just like the video did. And we look at the graph, so we can see delta K is marked in blue, delta UG marked in red, delta US marked in green, and delta E marked in yellow. And as you can see, the yellow is 0. Therefore, we can assume that there is no work done on the system. Energy is conserved. In order to compare this to the video, we import the CSV file, create a new ball, and create a new loop that will calculate the position for each time step. And then when we compare it to both, this is what you get for the x values, and this is what you get for the y values. In both the x and the y, the the data seems to, or the computer model seems to either overpredict a little bit in the X case or underpredict a little bit in the Y case. This may be due to a couple of reasons. First of course, we mentioned earlier that the time step in the video is a lot larger, so therefore it's not as smooth as you can see right here. All right here. Also, the code does not account for any outside force such as drag, which we know is acting on the video and the spring. Alright, so now we can go to our discussion questions. For the first model system, is the energy principle satisfied? So we have included the mass, spring, and earth to be in the system, therefore there is no outside work being done, so therefore delta E equals work, which is equal to 0. And this is in agreement with the graph of the energies of the system. As remember, the yellow line was just horizontal line on 0, and therefore the energy principle is satisfied. The next question is to compare and discuss the values for an oscillation period using both the X and Y values in tracker. So here are the formulas used to calculate that. A period of oscillation in the X was calculated to be 1.66 seconds, and a period of oscillation in the Y was calculated to be 1.52 seconds with an average difference of 0.14 seconds. So these two oscillations make up the ellipse-like motion of the mass. The period of oscillation in the X direction is similar to that of the oscillation of a pendulum, while the period of oscillation in the Y is a period of oscillation for a spring, and they are expected to have different values. In conclusion, although slightly off, the computer model did a good job representing the motion of the observed mass for not having accounted for any outside force. And starting from a fundamental principle, we can see that the net energy change of 0 is validated for this system. Thank you.